Welcome back to ECE 442-542. This is the next to the last lecture meeting. We will have a review session. It's not shown there, but the review session, I believe we've agreed before we started today to hold it at 5 o'clock a week from today. So add 7 days to today's date. That's the 11th. At 5 o'clock is the review session. I'll try to see if I can obtain a room, but it may be in the ECE building is what I'm thinking. Teacher course evaluations, you have, I didn't do my homework, did I? So I'll try to check before Wednesday's class what percent of the class has completed their teacher course evaluation. I don't need to see hands. But that's due on Wednesday by midnight, before midnight, the teacher course evaluations, and it is useful information for me to receive your input on teacher course evaluations. That's helpful for me for planning purposes, for not only the next time I teach this, but just in general, if there's something that I can change to improve the class or classes that I'm teaching. Final exam is a week from Thursday. It's the last day of finals, and it's during the middle of the day. It's right after lunch. It's at 1 o'clock, and it's a 2-hour final. And it will be comprehensive. We'll maybe talk a little bit more about that on Wednesday's lecture. And we'll talk a little bit more about it on the review session, which is scheduled a week from tonight. Homework number 8 is extra credit. That's due on the 7th. That's reading day, I believe. But the material on that homework assignment will be on the final exam. Whether or not you take the time to work the homework before it's due, that's up to you. It's extra credit for you, but you do need to know the material prior to the final exam. Here are the definitions that I am using, and here's what I hope to accomplish today. If I do not get to the last item, which is an example, or maybe I get started on that, I think I will just try to capture or extract something that I've already recorded maybe from a year ago and post that, and you'll have that in addition to tonight's lecture in preparation for homework number 8, if you think that would help you, and I think it will help you. But today what I want to cover is just review what we talked about quickly last time, which was the full state feedback. That's the input is a linear combination of all of the state variables. K can be a matrix. Not just a scalar. Unless X had dimension 1, or there was only one state component, that's when K as a matrix could be a 1 by 1 if we had one input. K could be a 1 by 1 matrix, which is a scalar. But generically, K is, if we have a single input, K is some row vector. And it's just weighting every one of the state variables, and we use that to try to arbitrarily locate the closed loop poles. The only time that we can arbitrarily move those closed loop poles is if our system is controllable, and we'll talk about what that means today. When can we take a system, by that I mean the system matrix phi and the input matrix gamma, from that information we can determine whether the system is controllable. If the system is controllable, then we can automatically know, independent of what K actually is, that we could actually position those closed loop poles wherever we want, and usually we want them to be positioned inside the unit circle. That's where they would be stable. If our system is controllable, then we have the ability to arbitrarily locate those closed loop poles. And the way I've been talking about it in this class is, why don't we just focus on 2 poles that dominate the response and locate all the others at the origin? That's the easy way to locate 20 closed loop poles. You just have to focus on 2 that dominate your response, and all the others are really fast. They're located at the origin. That's an easy way to do it. Now, in reality, you may not want to do that. You may want to make your other poles a little bit faster, or maybe complementary or helping some of your dominant behavior. But here, just to quickly come up with a design, I think that's a reasonable strategy. We will then talk about what we can do if we want to inject a reference input. Up to this point with full state feedback, we really haven't been worried about commanding our system to move to a particular location. Really all we've determined or done is adjust our closed loop dynamics. So how does our system respond to an initial condition? Or if you went up and kicked the system, how would it move to its equilibrium or to its stable state? How fast would that happen? That's what we're doing with K. If we now want to see or know where our system is going, we need to put a reference input in, so that now when we put a reference in, it will move with the same dynamics, but now it will move towards some final value, not just its, let's say, equilibrium state. Here is our review. Full state feedback, we now have a system matrix phi. That's the open loop system matrix. We have an input matrix gamma, and we have a output matrix H. That's really just how does our output measure these different state variables that are making up the components in X. And X could be 10th order. That means little n, Nevada, is now 10. X would be a 10 tall or 10 rows and 1 column. That's your state vector. In general, the input, you might have 4 inputs. Michigan, M is 4. U is now a 4 row by 1 column matrix. You have 4 inputs. Maybe you have a position input. Maybe you have a force input. Maybe you have a voltage input. Maybe you have a torque input. You have 4 inputs to your system. And those would then be making up the vector U at time, let's say L. And Y, that's Q tall, and that might be 3 output measurements, which are 3 different ways of linearly combining those 10 state variables X. Q is now 3, so that Y is this vector that's 3 rows tall and 1 column Y. With full state feedback, we are now interested in this feedback gain matrix, K, which is a matrix. Generically, with these dimensions, it's Michigan by Nevada in size. Most of the time in this class, Michigan is 1. Maybe you don't like Michigan being 1, but it's a number. Well, no. We're not playing a sport, so don't worry about Michigan being 1. Should have had something with an A, huh? Then Arizona could have been 1. But here is our block diagram depiction of that system, and including the full state feedback. And you can see that we are now going internal into our system. We are claiming, or we are assuming, that we have access to all of the state variables, and we can scale each of those by the elements in the K matrix and feed those back in to drive our system, and that actually changes our dynamic behavior. That's, I hope, the picture that you see when somebody says, oh, we're using full state feedback. Go back to an example that we were talking about last time, our phi matrix, and you should have all of this, and I will, as always, put it on D2L so you don't have to worry about copying everything down. I want you to basically understand what I'm scrolling through now. and we'll slow down when we start talking about controllability. But our phi matrix is 2 by 2 for the example that we illustrated. Can you, by inspection, tell me what the eigenvalues are without calculating them as I've shown here on the screen? You know what the eigenvalues are, since if you look at the bottom of the screen. But this matrix phi has a particular structure that allows you to immediately see the eigenvalues. This matrix phi is upper triangular, meaning below the diagonal everything is 0. In this case, everything below the diagonal is just a scalar 1 by 1. But if you have an upper triangular or a lower triangular or diagonal matrix, the eigenvalues are on the diagonal. In case you have a 2 on the diagonal and you have a 0 on the diagonal, those are your 2 eigenvalues for this system. You can see those by inspection. If you were on an interview and somebody said, here's a matrix, what are the eigenvalues? You go, oh, it's a diagonal matrix. Oh, it's an upper triangular matrix. Oh, it's a lower triangular. I know where the eigenvalues are. They're right on the diagonal. Or if you forget, you know that it's this determinant of zi minus phi, where the identity matrix is compatible with phi. That means the identity matrix is 2 by 2. We do the algebra. We take the determinant, which is just the product of the diagonals for a 2 by 2, minus the product of the off diagonals, and yes, we verified that the eigenvalues are indeed the ones on the elements on the diagonal, which are 0 and 2. And for this particular case, our system is not stable. We have one stable, and those are actually the poles of our system. If we looked at the open loop system dynamics, which is determined, if we looked at using the notation that I introduced just above, in terms of our matrices, our state matrices, H is the output matrix, phi is the open loop system matrix, and gamma is the input matrix. Our open loop dynamics, or our open loop system, is this capital G of Z. And if you look at Zi minus phi inverse, what's in the denominator is actually the determinant of that, and that's in fact what we use to compute the eigenvalues. The poles of that system are determined by the roots of Z times Z minus 2. If we now assume that we have access to all of the state variables, then we can apply full state feedback. And on Wednesday, we will walk through, present what happens when you don't have access to all of these state variables. What can you do? You can actually build an estimator and use the estimated states, and we'll walk through that basically with a block diagram so that you can start to see what might happen or how you could approach the problem. And that's actually a good way to give you another strategy for building a controller if you're struggling with, how do I control this system? I can't even figure out how to make it stable. Well, you can use these these state space techniques to just turn the crank and generate a controller, and now you go, oh, I wouldn't have thought to do that. And it will sort of suggest where you might put poles and zeros if you had these transfer function based controllers that you were interested in building. With full state feedback, this matrix K, that's our feedback, full state feedback gain matrix. We are using that to adjust the poles in our system. And we do that by equating the characteristic polynomial with K as a parameter, the different elements in our state space matrix K, or our feedback gain matrix K, and our desired characteristic polynomial delta sub D of Z. If we make that an equality, then we can solve by comparing coefficients, we can solve for k. In our example last time, we started with just this hypothetical set of complex conjugate pole pairs at 0.8 plus and minus j.2, and you could actually skip the first 3 lines and say, oh, I know because of the way these combine, if I multiplied these individual factors out, I can find this polynomial by just taking z minus 0.8, squaring that, and adding 0.2 squared. And that will then produce this second order polynomial that I want to achieve by selecting the appropriate gain values, k sub 1 and k sub 2, in this 1 by 2 matrix, or the full state feedback gain matrix K. That's the desired polynomial. That's this delta sub d. That's the right-hand side right there. Now what I want to do is I want to compute the other side, the left-hand side polynomial, which is this characteristic polynomial as a function of these unknown or yet to be determined k variables. And the k variables are those coefficients in your full state feedback gain matrix, capital K. Here I'm just saying, oh, that really is just Zi minus the closed loop gain matrix. We will eventually call this piece capital Phi sub C, which is phi minus gamma K. If we go through that algebra, then we're subtracting phi and adding gamma K, and gamma K is all zeros in the top row and 3 times K1, K2 in the bottom row, which gets added into the phi matrix to give us then the determinant of z minus 2 minus 1 in the top row and 3k sub 1, z plus 3k sub 2 in the bottom row. The determinant of a 2 by 2, you need to know that. You don't have to go out and buy a calculator to do that, I hope. And it might be easier to do it manually anyway with these variables, but you can do it if you have the appropriate calculator. You can do it symbolically and find this delta sub k of z, which is now what I was using for the left-hand side of that relationship. I now have these 2 polynomials. They're of the same order, and I can equate those, and that really just means I start comparing coefficients of equal powers of z, and that's going to allow me then to solve for the K1 and K2. I now end up in general with 2 equations and 2 unknowns for this 1 by 2 gain matrix, capital K. Comparing the coefficients that scale the z factor in this second order polynomial, I can find k sub 2 because it's the only gain in that equation, but in general there may be a k1 floating around and I may end up with 2 equations and 2 unknowns. Here they sort of allow me to do this sequential solving to obtain a pretty easy solution to the 2 equation, 2 unknown problem. Here I can solve for k sub 2 directly, and then I can look at comparing the constant coefficient terms z to the 0 and solve for k sub 1. That now allows me to put in the proper location, there's k1 and there is k2 in this full state feedback gain matrix K. And you can now use that to determine this full state feedback or the closed loop system matrix in your system representation. Here you have x at time L plus 1, x is your state vector, equal to phi x of L. That's your open loop dynamics. Now you're modifying that with feedback, and you're feeding back these two state variables in a particular manner. You're combining those two state variable components according to what you've solved K for. So that now capital phi sub C is capital Phi minus gamma K. We know phi, we know gamma from our system, and we just solved for K. We now know what capital Phi sub C equals. Now it's not so obvious what the eigenvalues are, because it's now no longer upper triangular, lower triangular, or diagonal. We've now mixed things up, but we've mixed them up in a way that hopefully the closed loop eigenvalues are where we want them to be. But you need to know how to find the closed loop eigenvalues. That's just the determinant of Zi minus capital Phi sub C, and it's a 2 by 2 matrix. That hasn't changed. The strategy is the same. And in so doing, we end up with exactly the polynomial that we wanted to. That was by design. That's how we solved for K1 and K2 to begin with, so that we now end up with this second order polynomial that we desired to achieve, and that gives us our roots at 0.8 plus and minus j.2. And these now govern our dynamic behavior of the system. Are these stable? If I gave you these roots on the final exam and I said, is this controlled system stable, what would you do if you, well, I would want more than just is it stable or not. That's a yes or no. That's too easy. That's a flip of a coin. I would want you to justify that yes or no answer. How would you justify whether or not these poles are stable or not? What's the strategy? You just look at the magnitude of these poles, and you want those to be having a magnitude less than 1. You want them inside the unit circle. You now have complex conjugate poles. You just have to calculate the length of one of those, because the other one's the same length from the origin. You now square 0.8 and you square 0.2 and add them together. Take the square root and hope that they're less than 1. And in fact, they are in this case. Is it clear that what I could ask you to do on the final exam with state feedback so far? I still have more to go. But do you feel comfortable building a K matrix? And do you know generically the structure of that K? Is it typically a row vector or a column vector? K. Is it short and wide, or is it tall and thin? Is it a row vector or is it a column vector, generally? If you have more state variables than you have inputs. It's usually short and wide, isn't it? If we have one input, it's a row vector, capital K. That leads us then to this notion of controllability. We just assumed that we could find a K to do what we wanted, which was to locate those poles arbitrarily. We want to now know, when is it possible, when we use full state feedback, to position these closed loop poles arbitrarily inside the unit circle. And that's really what your system will be controllable if that's true. So when is it possible for full state feedback to position the closed loop poles arbitrarily? When your system is controllable. And now what I'm wanting to do, or will do, is I will just tell you the result. We don't have time to verify this, but it's really, what it means to be controllable is it means that you can start anywhere with your state vector and arbitrarily move to another location in the state space domain by a finite or a bounded control. That's what it means to be controllable. In our understanding, it really means, can we locate the closed loop poles with full state feedback in arbitrary locations? Let me just give you what what you can use to verify whether a system is controllable or not. A system is controllable if and only if, now you feel like you've moved into a math class, but now you have this necessary and sufficient condition for controllability. You need the following matrix, I'm going to call it script C, to be of full rank. And I'll try to indicate what that means. But C, you just build it up. It's going to be your input matrix, gamma. Now you basically concatenate, or you pad on to that with some more columns. And the next set of columns that you pad on to gamma is the system matrix phi, the open loop system matrix phi, times gamma. Then you simply use that and scale it on the left with phi again, so that you now have phi squared gamma phi cubed gamma, and I think you get the idea. And you just keep going until you get up to phi to the Nevada minus 1 power. If your system matrix was 10 by 10, then you would need to go phi to the 9th times gamma. And you would have 10 sets of columns in this controllability matrix. That's what I'm going to call C. A system is controllable if and only if C is full rank. And this guy I may call the controllability matrix. For those of you that have had some math, what's it mean for a matrix to be full rank? Maybe what we should do to start is, what is this controllability matrix dimensionally? Suppose gamma, let's say we have 4 inputs and 10 state variables. What's the size of gamma? We have 4 inputs and 10 states. Dimensionally, what are the dimensions on gamma? Do you see where gamma is? Do you have this picture, mental picture of your state space representation? It's x of L plus 1 is equal to phi x of L plus gamma u of L. That should guide you in understanding the dimensions of gamma. Gamma has to be compatible with your state vector. How many rows are in your state vector? 10 if you have 10 components in your state. So gamma is 10 rows tall. It has the same number of columns as you have inputs. I said you had 4 inputs. Gamma is 10 by 4. So now if you think in terms of wood, if you wanted to go to Home Depot, you go, I need a 10 by 4. No, they probably wouldn't. They would look at you funny, but that's kind of the visual you need. You need something 10 by 4. Those are your dimensions. You now have a rectangle that's 10 by 4. It's actually a matrix that's 10 tall and 4 wide. That's gamma. Now, what's the dimension of phi times gamma? What is phi dimensionally? How big was phi? Or what do you know about the structure of phi? That's your system matrix. It has some particular shape. And if I said SpongeBob, would that help? Is that right? Is that the right name? Is it SquarePants? All right. So phi is square. Phi is always square. Now you have a 10 by 10 times a 10 by 4. What's that product? 10 by 4. So each of these partitions represent a submatrix that's 10 rows tall and 4 columns wide. So it's 10 tall and 4 wide, 10 tall and 4 wide, 10 tall and 4 wide, and we just keep going 4 wide, 4 wide, 4 wide, until we get to the 9th, but we started basically with 0. This seems like we're in C, doesn't it? We indexed with 0, phi to the 0, then phi to the 1, up to phi to the 9th, gamma. We have 10 of these packages of columns. This is now C is 40 columns wide and 10 rows tall. What's the rank of that? What's the maximum rank? Is that term even meaning anything to you? That's really how many linearly independent rows or columns you have in a matrix determines the matrices rank. In this case, you have a 10 by 40 matrix in this example. The most you can have in terms of linearly independent rows and columns is the smallest of those dimensions. You can only have 10 linearly independent columns or 10 linearly independent rows, and you'll have the same number. If you have 10 linearly independent rows, you have 10 linearly independent columns. That's the way these linear algebra things work. So we now need to make sure that we have 10 linearly independent rows or 10 linearly independent columns. And if we do, then that controllability matrix is full rank and our system is controllable, which means we can locate those 10 closed loop eigenvalues wherever we want inside the unit circle by the appropriate choice of the gain matrix K. And K in this case would be 4 by 10. Is it clear what we mean by full rank? Now, in this class, we said Michigan was 1, typically. If we have 1 input, then this collapses down, this figuring out the rank of the controllability matrix, and we can actually just check the determinant of this controllability matrix C and make sure that it's not equal to 0, for the system to be controllable. If you had a matrix C that's 10 by 40, you can't compute its determinant. That doesn't make any sense. It's only when a matrix is square that you can compute the determinant. When little m, when you have one input, now gamma, phi squared gamma, that's just one column wide. And now you have 10 columns and you had 10 rows. The C matrix would be 10 by 10. You could compute the determinant, and if it's non-zero, it could be negative, it could be positive, it just has to be not equal to 0, then you have 10 linearly independent rows or 10 linearly independent columns, and you have that controllability matrix being full rank. Let's look at an example based on our system. And based on our system, we already know the answer. Phi, well, technically maybe we don't. Maybe I picked those closed loop poles to be at a specific location that was possible. In fact, I randomly sort of selected those, so it was really an arbitrary choice of closed loop poles to be at 0.8 plus and minus j.2. Here was our system matrix, our open loop system matrix phi, our input matrix gamma. We now want to build this controllability matrix, script C, and that's gamma, phi squared gamma. He told me I needed to go to the 9th. Really? Do I need all of those for this example? How many columns do I need? What was little m? How wide is gamma? M is 1. What is n? That's 2. And this is n minus 1. Whoa. So that collapses down, doesn't it? All of this was just me going crazy. Our controllability matrix is just 2 sets of columns. The first one is just the copy of gamma, that's 0, 3. And now I need to post-multiply phi by gamma. And the special structure of gamma is 0, 3. That just means I need to take the last column of phi and scale it by 3. Is one way of thinking about that. You could do the matrix multiplication. You could say first row gamma, second row times gamma, but you will find that that ends up being the second column of phi scaled by 3. That's what gamma is doing. It's taking 0 times the first column and adding to that 3 times the second column. Now, can you tell by inspection whether C is full rank from this structure? You're looking to see, are my rows linearly independent? Or maybe I can see columns easier. Are my columns linearly independent? And they are, aren't they? Or if you can't see that, and if it had a little bit more structure to it, if it wasn't this clean structure for C, you could compute the determinant of that square matrix. That's possible. Now you take the product of the diagonals, which is 0 times 0, and subtract the product of the off diagonals and that says that our system is completely controllable. Questions on controllability? Now I could ask a question on the final and say, is it possible, maybe you've calculated in the first step of this 20-step problem, the first part is what are the open loop eigenvalues? And you could compute those for phi of the 10 by 10 matrix. Now you have to form this 10 by 10 determinant. So you found 10 eigenvalues of phi. I said, is it possible to move those to the following 10 locations? Those 10 locations are arbitrarily patterned in the unit circle. What would you do to verify that the answer to that question? One, you could say yes or no, but I might say justify your answer. How would you justify whether or not those poles could be arbitrarily located? You wouldn't have to find K explicitly. You could simply compute the controllability and justify your answer. Is that clear? You wouldn't have to solve for K. You could simply you could say, is my system controllable? If it is, then I can arbitrarily locate those poles inside the unit circle. If my system is not controllable, then I don't have total arbitrariness in where I could put those closed loop poles. So now I'm justifying that by simply saying that I'm justifying whether or not I can arbitrarily locate my closed loop poles by simply verifying whether or not this controllability matrix is full rank. That's all I've really explained to you in this class. And you can see that, or you could prove that to yourself by simply looking at a problem where you might say, let me try to control this system in n steps, and you'll actually see that that basically forces this controllability matrix to be non-zero in order to go from some location to another arbitrary location in your state space. We didn't really show that, but that's really what's going on. You simply need this matrix to be full rank. And with Michigan being 1, or with you having 1 input, it's all you have to do is check the determinant of that controllability matrix. Might be a 4 by 4 matrix if you had a 4 by 4 phi matrix. Let's say that we now have a system that's completely controllable, and we just start jumping up and down. Because now we can put our poles wherever we want. Wow, that was easy. Compared to before, we were stuck on this root locus, and that root locus depended on where I put my poles and zeros. How are we getting away with this? What's going on? What's the difference between full state feedback and these earlier transfer function based controller designs? Now what I want you to be thinking about is, how is this, wow, really? How is this block diagram different from our earlier block diagrams? What's different about this? One, this is in the time domain, duh, and the other one's in the frequency domain, but irrespective of that, what distinguishes this from our earlier transfer function based controllers? That's what I want to drive home now. In this particular system, we are assuming we now have the ability to measure 10 different variables, maybe, if our state was 10th order. if we had 10 state variables. Earlier, we were just measuring an output or outputs, one variable, and feeding that back. That doesn't give us as much flexibility, does it? And we were having to filter that one signal by these poles and zeros. We were designing a filter, it was called a controller, to adjust the closed loop dynamics. This full state feedback, the assumption is we can go in internally and measure all of these state variables. Position, velocity, voltage, pressure, temperature, whatever our state variables are, we're saying we can go in and measure those and feed them all back. That gives us a lot of flexibility. That's what we're assuming or having access to that we didn't have before, and that's why we can do so much with full state feedback. That's not necessarily a reasonable, practical assumption, and we'll try to show how we can deal with that assumption or not have that assumption holding in Wednesday's class. But for now, let's just sort of talk about the following question, which I tried to justify a little bit. Are we getting away with something? And what I tried to explain by scrolling all the way back to that block diagram is that with full state feedback, full state feedback requires access whoa, system's not stable, is it? Maybe you're not. You've been up all night trying to finish up your senior design project. I commend you for coming to class. Good luck tomorrow with your presentations if you are a senior. If you're a grad student, you can just kind of smile and grin. But you might want to go to the student union and show your support for your fellow classmates. Where was I? Oh, I was unstable with my T, wasn't I? My N and my T went ballistic on me. Full state feedback requires access to each component of the state vector. All of the positions, all of the velocities, whatever's making up our state vector. And now what we want to talk about, not only that, we might want to know, are there any other things to be worried about, or are there any other concerns? So let's sort of look at this block diagram again. Here is, and here I'm just using that additional depth to show you that this delay block is a bank of delays. If we had 10 states, we have 10 delays. That's all I'm meaning by that additional sort of half square around the delay. If that confuses you, don't even put it in there. But I'm just trying to emphasize that now we have a vector coming out of these delay blocks. Here is our state, x of n. Here is our state at time n plus 1, O. N is not the dimension of, well, do you see why I'm struggling with little n? I've been using little n to represent the number of components in my state vector. So let me just use L so that there's maybe less confusion. What makes up that state vector at one time step into the future is this combination of states at the present time and the input at the present time, which in fact is just this state vector scaled by minus k to form the input u of L. And maybe, well, we also have the linear combination of the states making up our output y at time L. What we've just told ourselves is if the system is controllable, then we can use that full state feedback gain matrix K to adjust the dynamics however we want. So K can adjust the dynamics of our system arbitrarily. We can now make our system dynamics whatever we want. We could really make it quick if we wanted, but you may want to be careful. You're not wanting to really hit your system hard or drive it really fast. So you may have some limitations on where you locate those closed loop poles. But theoretically, you can put them wherever you want inside the unit circle. What is missing here in this block diagram? And I hinted at it at the beginning of the lecture. I'm not sure it really made any sense. It may not make any sense right now, but hopefully after this little bit of discussion, it will start to become a little bit more clear. Let's say this system is stable. What's the output going to go to in the steady state? Now I can, if you thought of this as a mass spring damper system, I could pull that mass to some initial value. Maybe I could even start it with some initial velocity and let it go. And I just said it was stable, so what's going to happen to that mass? It's going to go to its nominal location, which let's just say is 0. It's going to go to 0, isn't it? No matter where we start with our initial condition. That's kind of boring, isn't it? Does everything have to go to 0 if we're controlling it? That would be pretty plain. So we want the opportunity or the ability to inject an input that could command the output to go to some other location other than the origin. And we don't have that right now. We do not have an external reference input. We've just made our control, U, a linear combination of the state to arbitrarily manipulate the dynamics. That's good, but we're only going to the origin all the time. In this block diagram, there is no way to provide a command signal to the system. And this is actually called really a regulator. You're just regulating this system's dynamics. This is a regulator system. And that's good because it allows our system to have the desired dynamics that we want in terms of how it shakes to its final value. System has desired dynamic response. To wherever we start or to our initial conditions. What would be nice is if we could now command this system to move to other locations other than just the origin. Or can we introduce a reference input? And don't you wish that I asked that question on the final? Can we introduce a reference input? Flip of the coin. How many people thinks it's yes, and how many think it's no? Thumbs up if it's yes, thumbs down if it's no. 1, 2, 3. Some of you are kind of in the doldrums, huh? You're answering no. I wouldn't have asked this question if the answer wasn't yes. Okay? It would have been pretty boring if all life went to the origin. In a controls class, if all we could ever do is go to the origin with full state feedback, we'd be in pretty plain company, wouldn't we? Oh, we're going to fly this plane. Where? To the origin. Where are we going today? To the origin. Where are we going today? To the origin. Could sell too many tickets, could we? Unless the origin's a fun place, and it is in the Z-plane, that's okay, but it's in the state space, isn't it? Now every variable is 0. That's kind of bland. The answer then is yes. Can we introduce a reference input? And really what we're doing is we're coming back here and we're changing this a little bit. We're now saying, oh, we're going to now not only put this guy in, now I've run out of space, but you could say, oh, let me put a reference in and scale that, let's say by n sub 1, and now I can inject a reference R into that and hopefully drive my output to someplace other than the origin. That's the idea. We've already figured out how to pick K. Now we want to know, how do we pick n sub 1? And if U is scalar and R is scalar, n sub 1 is just a scalar. I've made it look like a capital N sub 1. It's a matrix, but it's a 1 by 1 matrix. We want to know, how do we pick n sub 1? If you had to guess, put in, let's say I'm steering a telescope, and I say, go to 10 degrees. I put in that command for R. What do you think I want Y to do? Go to 10 degrees. I now say, I want to go to minus 15. You probably want Y to go to minus 15. How do you make that happen? You try to make n sub 1 such that the DC gain between R and Y in this closed loop system is what? 1. You want a DC gain in this closed loop system between R and Y to be 1. You picked K to give you the dynamics that you want. Now it shakes to 10 the way you want it. Now you need to pick n sub 1 to give you the DC gain that you want. So let's go through the algebra to make that happen, or to figure out how to pick n sub 1. Is it sort of clear what we're doing? Before we didn't have this, did we? This guy, I've just added in. That's the extra piece. That's the reference input there. Let's now talk about the algebra needed, or that we can work through if we have a reference input. with state feedback, and I hope it's clear what I'm wanting to do. I now want to command my output to go somewhere, and I want it to go exactly where I tell it to go without any error. And for this discussion, let's go ahead and assume a scalar input, or only one input. What we're saying is we now have U of L is not only our full state feedback, but in addition, it's some reference input combined with our full state feedback. That's what's happening at this location for U sub L. That's just N1R plus minus KX. And that's what this is saying. That's our full state feedback with a reference input. That's what we're doing with that choice of U of L. If we had one input and four states, what does this look like? I would just draw a picture. I would say, oh, U, I have one input. That's just this. It's a scalar. What does K look like if I have one input and four states? What are the dimensions on K? I want you to start seeing this, or if you don't see it, just put it, sketch it, draw it down. What does K look like? Is it short and wide, or is it tall and thin? One input, four states. I hope you said K is going to look like that. It has one row, four columns. X, those are just generic numbers. What's the size of capital N sub 1? It's 1. R is 1. Those two products on the right give you two scalars which you can linearly combine to produce the input to the system, which is a scalar. And N1 don't have to have the same dimensions. That's what I'm hoping to drive home with that graphic. Here's our system. We now have X at time step L plus 1 is phi X of L plus gamma U of L. That's our system. Our input, which is full state with reference input, is U of L is equal to minus K X of L. That's the full state part, plus N sub 1 R of L. Let's now just replace little U of L with what we've defined it to equal. This now says that if we close the loop, or if we combine these two equations, X at time L plus 1 is phi X of L plus gamma times minus K X of L plus N sub 1 R of L. Everybody okay with that? This piece right here is just U of L. If I now put some of these pieces together, do you see that I have two terms that are multiplying or pre-multiplying X, my state vector? I have phi making or hitting X, and I have minus gamma K hitting X. I can now pull the X out, and I now have phi minus gamma k x of L. That gives me that and that piece. And I have remaining plus gamma n sub 1 R of L. And possibly to shorten my notation, I might just call that combination capital phi sub c. That's my closed loop system matrix. And that's going to be having eigenvalues where? Where are the eigenvalues of phi sub c? It's a pretty vague question, but those depend on whether your system is controllable. If your system is controllable, then you have arbitrary freedom over the eigenvalues of phi sub c. You could pick k to give you those desired closed loop poles for the matrix phi sub c. Let's say that we've done that. Now we have a phi sub c matrix. We have gamma. We don't know what n sub 1 is. We also know that our output equation, y of L, is equal to h x of L. And what did we say about n sub 1? How did we want to find n sub 1 or pick n sub 1? Remember the block diagram? We wanted the transfer function between r and y to have a DC gain of 1. We now need to find the transfer function between little r and y. And we have all of the equations to do that. The only thing we don't know is n sub 1. That matrix, which in this case is a 1 by 1 matrix, it's a scalar. If we have one output and one input. So now let's find the transfer function from the reference input R, which I'm going to call capital R of Z, to the output Z transform Y of Z. Now I can just simply Z transform this system of linear difference equations. What happens when I Z transform little x at time L plus 1? This is a review for the final. That's a pretty easy question. This is now just Z times capital X of Z. That's equal to the closed loop system matrix phi sub c times the Z transform of X, which is capital X of Z, plus gamma n sub 1. Those are all just constant matrices, so the Z transform you can just slide through and find the Z transform of our reference input, little r, which is capital R of Z. We can Z transform the output equation. That's just y of Z is equal to h x of Z. We can combine the terms that involve capital X of Z here, remembering we can inject that identity matrix there, and we now have Zi minus phi sub c X of Z equaling gamma n sub 1 R of Z. That was just that equation, putting the capital X of Z terms on the right. We can now solve for capital X of Z by inverting that matrix on the left, or pre-multiplying both sides by Zi minus capital phi sub c inverse. And we can now use this x in there to provide us with capital Y of z is now h times zi minus phi sub c inverse gamma n sub 1 r of z. Did everyone follow the algebra? You've done that algebra before. Nothing new. It's just now you're doing it with a gain on your reference input. And the closed loop transfer function is now that expression t sub c of z. And what you just told me earlier is that we want to select this scalar n sub 1 in such a way for t sub c of z, that transfer function, to have a DC gain of 1. How do we find the DC gain of a transfer function? What's the magic z? Where do we evaluate the transfer function if we're interested in its DC behavior? If you did this in the Laplace domain, we would be at the origin, wouldn't we? We would be saying s is equal to 0. But here, s equals 0 is consistent with z equal to 1. We now are wanting to look at t sub c of z with z equal to 1, and we want to set that whole thing equal to 1. There's our formula for t sub c of z. If we replace z with 1, now we just have the identity matrix, phi, or I minus phi sub c, and invert that. Our formula now says that we can have h times I minus phi sub c inverse gamma n sub 1 is equal to 1, where I've essentially replaced little z. I've evaluated that expression t sub c of z with z equal to 1. If I now have one output and one input, I might abbreviate that as SISO, and that's what you would say. It's an SISO system. You wouldn't say SISO. Somebody might kind of think you were a little different if you said, I have a SISO system. Actually, some people do say in MIMO for multi-input, multi-output, MIMO, so I guess you would have a SISO. But SISO, single input, single output, that means that this expression, H, I minus phi sub c inverse gamma, what do you know about that as a quantity? What are the dimensions on that? If you have one output, H has how many rows? 1. If you have one input, how many columns are in gamma? 1. Now you have a 1 by 1. That's a scalar. That's just a number. You can divide by that scalar, and that's going to be really your capital N sub 1. This is a scalar. Therefore, you can divide it out. All of those are known, and N1 is just 1 over that scalar. for a single input, single output system. You can do that algebra, invert that number, and that's now what your n sub 1 is. I will post an example of this working with a mass spring damper system to illustrate this, maybe with some MATLAB commands. That's in addition. I don't think you want to be here another hour, so we won't do that tonight. But I'll see you on Wednesday, and we'll start going a little bit further with maybe some of these assumptions. What happens when we want to get rid of this assumption that we have access to all of these state variables? We'll pick up at that point on Wednesday.